All right, so we're going to continue looking at section 6.1. Today, one thing that's very important we're going to need to know from the first half is how to change degrees to radians. Okay, we're going to use that right off the bat in our first formula we look at. Okay, so first part of this section focuses on finding the length of an arc. Okay, so an arc is just part of a circumference of a circle. And one thing that's going to help us to do this is the fact I wrote on the board. The size of an arc and the size of an angle are directly proportional. Okay? Which means if I double the size of this angle, I double the size of its arc. If I make this angle half as big, I make the arc half as big. Okay? So there's a direct connection between the size of the angle and the size of an arc. Make one bigger, you make the other bigger. Make one smaller, it makes the other one smaller. Okay, so any questions on that idea? Because everything I do in this formula is based on that. All right, so what I've drawn here is a diagram. Okay, this time I've drawn two angles. Okay, I called one angle theta and the other one theta 1. Okay, and both of those angles have arcs associated with them. Okay. If you look at the rays for theta, where they hit the edge of the circle, that defines our first arc, which I'm calling S. Okay, and then theta 1, look at where the rays of that hit the circle, and that defines our other arc, which I'm calling S1. Okay, any question on the diagram? All right, now, our goal is to come up with a formula to change, basically, or to figure out the length of an arc based on a couple different things. Okay? One, it's going to be affected by the size of the circle. Okay? Bigger circles have bigger arcs. And it's affected by how big this angle is. Okay? Those are the two things that affect it. So, like yesterday, we've got to come up with what I call a starting fact. Okay? Here's a starting fact we've looked at before. And if you know that fact, you could set up a proportion to convert feet to inches. Okay. 1 foot, 12 inches. Okay. On the other side, you just set it up the same way. Feet, inches. Okay. Let's say somebody said, I want to convert 80 inches to feet. I just put 80 right there, and I put x right there. And with a proportion, you cross multiply. But this is all based on knowing that fact. Okay? If you don't know this, you can't figure out anything. Okay? So you gotta have to just know this already ahead of time. Same idea here. We have to know something ahead of time. Okay? And something we learned yesterday is going to help us. Does anybody remember when I drew the diagram of a radian? If this was 1 radian, okay? Suppose this angle was 1 radian. The size of this arc would be the same as something else in the circle. Does anybody remember that? Only if this angle is 1 radian. The size of this arc would match. Radius? Yeah, it would match the radius. Okay? There's our in 1 foot, 12 inches. Okay? That's a fact we know, and we can use it to figure out other things. Okay, so suppose that theta 1 is 1 radian, then that means this arc, S1, is automatically the same size as the radius. Without that fact, that's like being without the 1 foot, 12 inches. We're stuck. Okay, we can't do anything. Okay, but now that we have that fact, we can set up a proportion. And what I'll do is set it up like this. I'll compare theta 1 to S1, and then I'll compare theta to S. Okay? You can set up the proportion a lot of different ways as long as you're consistent. Put the angle on top, arc on the bottom. Angle on top, arc on the bottom. Just like when we do feet and inches. Feet on top, inches on bottom. Feet on top, inches on bottom. Set it up the same way. And now fill in theta 1. Okay, we'll plug in 1 and fill in S1. We'll fill in R. Right, so that's going to give me 1 over R equals, now the other side we don't have anything. That would be the side that you plug stuff into from the problem. They'd have to tell you, in this type of case, the feet and the inches. Okay. So for now, just leave them. We don't have any other information. Okay, and how do we solve a proportion? What do? We cross multiply. So I'm going to do S times 1, which is S, and I'm going to do R times theta. S equals R theta. Okay, that's the formula for how you find the length of an arc. S equals R theta. So S is the arc length, R is the size of the circle, it's the radius, and theta is your angle. But what did we assume about this angle way back at the very beginning of this formula? Radians. Yeah, we assumed radians. Okay? So that means when we use this formula, the angle has to be in what? Radians. Yep, it has to be in radians. Okay? Can't use this formula with degrees. Okay, so the way this formula works, you've got 3 variables. They'll give you 2 out of 3, and you find the third. So they could give you R and theta. They could give you S and R. Or they could give you S and theta. Okay, but whatever they give you, plug them in, and you find the third thing. Okay. Questions on the formula? Okay. Yep.
So you can't do this if you don't have 1 over 3?
No. No, it'd be kind of like if I gave you a distance rate time problem, and I just said I traveled 800 miles. How fast did I go? You need a little more information. If I said I traveled 800 miles in 8 hours, then you could figure it out. Okay, but you got to have 2 out of 3. All right, so this one says find the length of the arc. Okay, so that first part of the sentence right there tells me what letter I'm solving for. Find the length of the arc if the radius is 2 and the angle is pi over 4. Right, so for this problem, I drew it out. You don't need a sketch. You won't get a sketch in every problem. Okay, somebody just remind me, what's my formula that I'm going to use?
At equals R cube or theta or theta?
Theta, yes. S equals R theta. All right, so we're finding the length of the arc. Okay, we don't know that. That's S. Okay, Kyle, what's my radius here?
2. Well, 2 inches, but...
Yep, you're right. We're going to come back to that at the end. We're going to make sure we put the right label. So keep in mind that was 2 inches. And what's my angle? Yep.
Pi over 4.
Now, is that in radians or degrees?
Radians.
That's in radians. We're good to go. Just plug it in just the way it is. Okay, and multiply it out. 2 times pi. It's 2 pi over 4. And if you can, just reduce what you can. What's 2 pi over 4 reduced to? Pi over 2. Now, we just found a length of an arc. In this problem, what are my lengths measured in? Radians measure angles. Inches. Okay? So radian, that's for measuring the size of an angle. Inches is for measuring length. Okay? And that's it. If they want a decimal, we could type in pi divided by 2, and it's about 1.57 inches. Okay. Any questions on how we found the length of that arc? Okay, this one's a little different. What's it asking me to find this time? Radius. Okay, so I'm not going to know R. So if I'm not going to know r, they've got to tell me the other two things. They said the arc length is 3 pi, and the central angle is 60 degrees. All right, so Pat, what's the formula I use again?
S equals R times theta.
R times theta. Okay, now we're going to fill in what we know. Okay, Tyler, what is this 3 pi feet? What letter does that go in for?
Isn't that for the radius?
No, in this one we're going to find the radius. So we don't know the radius.
The arc length.
Yeah, it says the arc length is 3 pi. Okay, so which letter here is my arc length?
S.
S. Okay, so I'm going to fill that in for S. R, I'm just going to leave as R. I don't know it. And what's my angle here? Yep, 60. So where do I put that in?
Right after R.
Right after R?
Yeah, but you have to convert into radians.
It has to be in radians. Okay, remember that angle has to be in radians. So first thing I have to do is change it. If I put it in as 60, it's wrong. Okay? So 60 degrees. Okay, what do I multiply by to change that to radians? Good, pi over 180. Degrees is gone. 60 goes into itself once. 60 goes into 180 3 times. Pi over 3. Okay. Any question on that? Okay, so last thing I have to do is get r by itself. And there's a way I can get rid of the pi and the 3, both at the same time.
0 pi.
Multiply by the reciprocal. 3 over pi, 3 over pi. So the pi's are gone, 3's are gone. How about on the other side?
9.
Just 9. Okay, pi's are gone. And the radius is 9 what? Feet. Okay, remember, radius is a length. Okay, you never say the length of this table is 150 degrees. That doesn't make sense. Okay, so any lengths have to be measured in feet or inches, centimeters, whatever. Angles are always measured in radians. If they're not, change it. Okay, any questions on that? All right, anybody need me to go through the third type of problem you could have? That's where you'd be solving for the angle. So if you had one where you're solving for the angle, I just have to make one up. It'd say something like the radius is 6 inches. The arc length is, let's just say, actually, you know what? Let's make it smaller. Let's make it, yeah, it doesn't matter. You can make it any size you want. Okay, find the angle. So I just fill in what I know, and I'd solve for theta. S equals R times theta. And how would I get theta by itself?
Divide by 6.
Just divide by 6. And that's it. You're done. Okay. If you can reduce it, reduce what you can. Now, what would be the label on this?
Inches.
Is this a length? It's an angle. So the label would be radians. All angles are measured in radians. Remember, we don't use degrees in this formula. So do I have to write RAD? No, I'm done. That's pi over 2 radians, okay? Because it's equal to an angle. That's not a length. These were my lengths. 6 inches and 3 pi inches. Okay, so that's the third variation you could have of that formula. Okay, so that's it for arc length. Okay, so today that's kind of what we're going to do. We'll look at like a concept. It's a pretty short, simple thing, and then we'll look at the next part. All right. So the last part of This section is angular velocity. Okay, angular velocity is used to measure the speed, but it's usually used to measure the speed of something spinning in a circle. Okay, anybody think of something in real life where the speed of something spinning is measured? Yep.
Like the carnival rides, like they go around in a circle, like the trains.
Okay, you could measure like a Ferris wheel, how many like revolutions per minute it makes, or like a merry-go-round, something like that. You could measure it, but there's some other ones that we measure, and it's really important to know for certain reasons. Yeah, engines. Okay, engines are usually measured in revolutions per minute. They usually call it RPMs. So if you have a tachometer on your car, you can see that, and there's certain limits to how high that engine can go. You've got to be careful if you push it too hard. Bad things happen. All right, so we measure that. Sometimes power tools, like if you look at them, they might be measured in RPMs, how many revolutions per minute they spin at. All right, so first of all, why even bother with RPMs? We already have a way to measure speed. Okay, like miles per hour, feet per second. Why don't we just use that? Right? So I want you to take a look at this diagram. Okay, I've got 3 dots on it. Okay, I want you to watch what happens as I spin it 1 full revolution. Okay, just watch what's happening to the dots. Okay, which dot traveled the farthest? The outside one. If you look at the one on the inside, it didn't really, well, if it was at exactly the center, it wouldn't move at all. Okay, it would just stay right where it is.
So we went a little bit. It looked like it was moving a little bit.
Oh, it might not be exactly in the center. So this is our formula to find the speed of an object when we're just using linear speed. Okay, like Tyler asked me about earlier. If you know your distance and you know your rate, you can figure out how long it took you to travel. Well, everybody just agreed that this dot was traveling the farthest, right? Now, what was the difference in time it took for all of them to get back to their starting point?
It's the same time.
It's the same time. Okay? So they all took the same amount of time to get back to their starting point. So what does that mean? If this thing traveled the most,
Go faster.
it's going faster. Okay? This dot is going faster than this dot, which is going faster than that dot. Okay? Because this dot traveled the farthest in the same amount of time as everything else. So like if all your friends were driving somewhere, and after an hour you drove 100 miles, another friend drove 80 miles, and another friend drove 60, well, if you drove 100, you must have been traveling faster because you went farther in the same amount of time. Right? So that's what makes this confusing. All these dots are traveling at different linear speeds. The further you get out from the center, the faster it's going. So to simplify that, instead of talking about these speeds in terms of linear speed, we use angular speed. Then I can say every one of these dots made a revolution in 2 seconds. Every one of those dots made 1 revolution in 2 seconds. Some revolutions were bigger than others, but they all made a revolution. Okay, so it gives a common speed to all the points on that circle. That's why we use angular speed. All right. So in the book, when they ask for angular speed, they're going to want it in radians per time unit. Could be radians per second, radians per minute, radians per hour. The time unit is not what's important. They want it in radians. Okay, again, real life we usually use like revolutions. That's more common. But we're going to practice with radians. Okay, and the other type of speed I mentioned to you, that was linear speed. And that's the speed traveling in a straight line. Okay, like you see on your speedometer. Feet per second, miles per hour. On European cars, kilometers per hour. Okay, Okay, and what we're going to do is just practice converting between different units. Okay, so we'll start out with really simple conversions that aren't even anything to do with trig, like just convert seconds to days, and then we'll get into a little bit more complex ones. Right, and the way we're going to do it is with dimensional analysis. Okay, you guys have already been doing this when I taught you how to change radians to degrees. I asked you, where does degrees have to go to cancel? So you think about your units, and you look at where it has to go to cancel out. Okay. So any questions on what we're going to try to do? All right. So the first one, this isn't even a rate. It's just a number. Just convert 3 days to minutes. That's it. Right, so I'm just going to start by writing 3 days. Okay, to convert days to minutes, what we're going to do is we're going to multiply by conversions. Okay, you need to know common conversions. Days to hours, hours to minutes, minutes to seconds, inches to feet. Okay, all those basic things you need to know. And we always go one step at a time. So what's the next unit smaller than a day?
Hours.
An hour. Right? So in 1 day, how many hours do we have? 24. Okay, and let's write out the other conversion while we're here. What's the next unit smaller than an hour? A minute. All right, so in 1 hour, there's how many minutes? 60. All right, so those are the two conversions you need for this problem. All right, so now, first thing we're going to do is convert days to hours. So we're either going to multiply by 24 over 1 or 1 over 24. Okay, and the way we figure it out, we want days to cancel out. Think of days as being in the top. Where does days have to go to cancel out? Bottom. And the number with days is 1. The number with hours is 24. So now days is gone. Okay, now we want to get hours to cancel out. Okay, where would hours have to go to cancel out? In the bottom. Okay, so that means minutes is going to go in the top. Now we need the conversion between hours and minutes. So we look it up. 1 hour, 60 minutes. Hours in the bottom, hours in the top. And now our last step, look at your units. All you're left with is minutes, and that's what they wanted. Okay, so now just multiply it out. You go straight across. So it's 3 times 24 times 60. All right, so 3 times 24. So we get 4,320 in the top. Now in the bottom, we'd put divided by 1 times 1 times 1. So in this case, there's no denominator. It's just 1. So I don't have anything to worry about there. If I had numbers that weren't 1, I would multiply those together, and I would put that in the bottom. Okay, so that's the first one. Any question on changing days to minutes? Yep.
Yeah, for the first one, for like 3 over 1, so it's like for 3 days or over 1 what? Like
There's no unit there.
just 1.
Yep.
Right?
Just 1. Just the number 1. No unit with it.
Would there ever be a unit there? Or would...
Yes. So for this problem, we have, it's a rate. We're traveling 50 feet every second. Okay, that's our speed. 50 feet per second. So now when we write this one out, we're traveling 50 feet in 1 second. Okay, there was no unit to this number in the bottom when we had the 1 with the days. It was just 3 days, just not 3 days per week or 3 days per year, it was just 3 days. That was it. All right, so this one we have 2 units we have to change. We've got to get feet to miles, we've got to get seconds to hours. Okay, and it doesn't matter which way we do it first. So you want to deal with the length first or the time first?
Like,
Length. All right, so we're going to get feet to miles. That's one conversion. We go directly from feet to miles. Even if you don't know the number, where does feet have to go? Top or bottom? Bottom. I'm trying to cancel it out. Miles is going to be in the top. So in 1 mile, how many feet are there? 5,280. Okay, you need to know that. In 1 mile, 5,280 feet. Okay, now feet is gone. If we stopped right now, our speed would be in miles per second. All right, now we want to get seconds to hours. Okay, so what's my first step to get seconds to hours? What do I got to get it to?
60 minutes to 1 hour.
We got to get it to minutes. So Upi said 60 seconds to 1 minute. Upi, do you want to put seconds in the top or in the bottom? Top. Good choice. Because we want to cancel out seconds. So he said 60 seconds in 1 minute. Seconds, seconds. Now our speed would be in miles per minute. Okay, we got to go one more step. How do we get minutes to hours? Yep. 60 minutes in 1 hour. Okay, so all you're doing is using conversions all the way down. Make sure your units are one in the top, one in the bottom, so they cancel. Okay, now we multiply it out. This time I do have a denominator. Okay, so let's just see what we get. So 60 times 60 is 3,600 times 50 divided by 5,280. Okay, so that's a speed of about 34.09 miles per hour. And you can write mph, or you could just write miles per hour. That's fine. Okay, any questions on that one? All right, so the last type of conversion. Okay, I want to convert radians per second to revolutions per minute. Okay, so now this is kind of getting into what we learned yesterday. Okay, this object is spinning at 200 radians every second. Okay, so there's 2 units we got to deal with. We got to get seconds to minutes. Okay, we've done that. And then we have to change radians to revolutions. Okay, what's my conversion to get seconds to minutes? 60.
16 seconds in 1 minute.
60 seconds to 1 minute. And I made it so seconds was in the top, so it cancels seconds in the bottom. Okay, so we got our time, minutes. And now I want to convert radians to revolutions. Where's radians going to go? Top or bottom? Yep, goes in the bottom. Revolutions in the top. And now we got to remember this from yesterday. In 1 revolution, it's 360 degrees. Or how many radians is that? 6.28, or what is it exact? But that's correct. 2 pi. Okay. So that's one we need to know. In 1 full circle, 360 degrees, 1 revolution, it's 2 pi radians. Okay. And now just multiply straight across. So we have 200 times 60. Okay, divided by 2 pi. So I can do divide by 2 and then divide by pi, because this calculator, it's hard for me to type stuff in on. And that's 1,909.
A lot of decimal ones.
Yeah, we'll round it to 0.9.
Okay.
Okay, 1,909.9. 1,909.9. And that's revolutions per minute. So that's pretty fast. I mean, some engines, go up to 8,000 or 9,000 RPMs, but that's 2,000 RPMs might be what your car idles at. Maybe. Okay, any questions on that? All right, so let's see if we can do this one. Okay, and then this is going to be it for angular velocity, and then we'll look at our last thing for today. Okay, so this one says it's a wheel that has a radius of 18 inches, and the wheel is spinning at 1,850 RPMs. Okay, first thing I want to do is just convert RPMs to radians per second. Okay, and then the next thing I want to find is the linear speed at a point on the circumference of the wheel. Kind of like I was spinning that wheel earlier on the board. I want to find the speed of a point right on the edge of the wheel. So what this basically means is if this wheel was spinning at 1850 and you put it down on the ground and it didn't lose any traction and it just took off, how fast would the wheel be going? Okay, that's it. Okay, another way you could think of it, same type of problem. Little kid has a rock tied to the end of a rope, 18 inches long. He's swinging the rope at 1850 RPM. If he lets the rope go, how fast is that rock going to take off? That'd be pretty dangerous. But that's exactly the same thing we're doing here in part B. Okay, just a different way of visualizing it. All right, so let's start with part A. Find the speed in radians per second. What is that 1850? They wrote RPM. What's that stand for? It's 1850 revolutions per minute. Okay, do we have to change our time unit here?
Yeah, the seconds.
Yeah, we got to change it to seconds.
So 1 minute.
So,
instead of 60 seconds.
yep, in 1 minute, 60 seconds. You made a good choice. You put minutes in the top, so it canceled out. Okay, and now we need radians. Okay, where's revolutions going to go? Bottom. And in one revolution, how many radians? 2 pi. Okay, and that's it for part A. Just multiply it out. So we have 1850 times 2 times pi. And then divide by just 60. Yep. So it's 193.73 radians per second. Now sometimes they have you do part A because it helps you with part B. Not in this case. Okay, part A was just a separate question. It actually has nothing to do with part B at all. All right, now let's look at part B. We want to convert revolutions per minute to feet per second. Okay, so we're going to start out the same way. But something different is going to happen here. Okay, something we haven't done yet. Okay, let's just get minutes to seconds. Okay, we can do that part first. 1 minute, 60 seconds. Now, what's the difference between measuring a speed in radians per second versus measuring a speed in feet per second? What are we doing here? Versus if I said measure it in feet per second, miles per second, kilometers per second, that's all the same kind of thing.
Well, isn't feet per second like a linear speed?
That's linear, yep. And what about radians per
Radians
second?
per second is angular.
Angular. So we're making a jump here from angular to linear. Okay, we haven't done that yet. Right. So anytime you want to make a jump from angular to linear, it's always best to have your speed in revolutions. Okay? Revolutions is the kind of the jumping off point that helps us go from angular to linear. So our goal, I know I want revolutions in the bottom. Okay, and let's just look at a piece of information we haven't used yet. The 18. Okay, I haven't used this yet. We're going to use that right now. Okay. Now, eventually, I have to get feet. So I could either change 18 inches to feet right now, or I could do it in inches and then change it at the end. So do you want to change 18 inches to feet now, or do you want to change it later? Now. Okay, so we'll change it now. Okay, easiest way to take something in inches and change it to feet is divide by what?
12.
Divide it by 12. It's 1.5 feet. Again, you don't have to do it now, but if you don't do it now, you got to do it later. Okay, so that's the radius of this wheel. It's 1.5 feet. So my goal is to figure out how many feet in a revolution. Okay, well, on a circle, what do we call one full revolution?
The circumference.
It's the circumference. And what's the formula for the circumference? 2 pi r. What's my radius in this case? 1.5. So the circumference of this wheel is 2 pi times 1.5. What's 2 times 1.5? 3 pi feet. So in other words, if you had, think of it this way, if you had a string, okay, and you made it in the shape of a circle, and it had a radius of 1.5 feet, and you cut the string, and then you laid it out flat, it would be this long.
So we're not really times the amount of power we're using as.
Yeah, well, it's 3 times 3.14, but we're just not rounding it.
All right, because if you put down the calculator, it goes to like 9.42.
Yeah, don't round it off. Yeah, leave it just like that. Okay, so it's a little over 9 feet long. Okay, so now we know how many feet are in one circumference. And a circumference is exactly the same as a revolution. So there are 3 pi feet in one revolution. So if you took this tire and you marked it, you put it on the ground, and you rolled the tire 1 revolution, and then measured the distance the tire rolled on the ground, that's how far it would roll. 3 pi feet. Or a little over 9 feet. So pretty far. Okay. So now we've got revolutions is gone, minutes is gone. And we're left with feet per second. Okay, so we'll multiply that out. This conversion you have to be careful with. It's different for every problem. It depends on the size of the tire. Converting minutes to seconds, it's always the same. Converting miles to feet, it's always the same. Never changes. But this conversion will change depending on the size of the tire. Okay. That's the first time we've seen a conversion that can change. Every other conversion we've done so far, always the same. Seconds to minutes, never changes. It's always the same. All right, so let's see what we get. We got 1850 times 3 times pi, and divide by 60. Okay, so this tire is traveling at 290.6 feet per second. It's pretty fast. Okay, any questions on that? All right, so that's our second thing. Probably this is probably the hardest thing today, just keeping all the units straight. All right, so last thing, but we're not going to finish this today. Okay, so unit circle trig. All right, this is going to be the first time in this class that we actually see the trig functions written out. Okay, there's buttons for them on your calculator. Okay, we haven't talked about them yet. Okay, you might know what they stand for. Okay. But you probably haven't done trigonometry on what's called a unit circle. Okay, so the idea of unit circle trig is very simple. What I've drawn right here is an angle. That's the initial side. That's the terminal side. The terminal side hits the edge of the circle somewhere. Where does it hit it? Well, it depends on the size of the angle. If it was 90, no, it would hit it up here. If it was 180, it would hit over here. But the point is, every angle that we draw on this circle, you can draw the terminal side, and the terminal side will hit the edge of the circle somewhere. Any question on that? Well, this somewhere is very important. Okay? If we can find the coordinates for where this point is, then we can do everything we need to do with unit circle trig. So the whole goal of this is to be able to find the coordinates for where the terminal side hits the circle. That's it. That's unit circle trig. And that's basically what I've written out right here. Okay. We only use unit circle trig with certain angles. Okay. We're going to do it with angles that are multiples of 30 and 45. This is not a tool you use for every single problem. Only for angles that are multiples of 30 and 45. Okay, so what you do is you sketch it. We're going to sketch it on a unit circle, hence the title of the section, unit circle trig. And we're going to look at where that endpoint of that arc is. Okay, right here. It's right where the arc ends. It's where the terminal side hits the circumference of the circle. Well, that endpoint has a coordinate. It has an x value, it has a y value. If we can find those values, they're going to allow us to be able to work with what's called the 6 trigonometric functions of our angle. And some of you might already know the names of some of them. There's buttons on the calculator. But that's the general idea. So any question on the general idea? Okay, the short version is you have to find the coordinate. Okay, that's what you have to find. All right. Does anybody know some of the trig functions, like what their names are? Yeah, is sine. I heard that one.
Tangent.
Tangent, that's one. Cosine. Those are the 3 basic ones. Sine, cosine, tangent. Sine is abbreviated SIN, cosine COS, tangent TAN. We're going to use these functions in every chapter of trigonometry. Okay? These are fundamental to everything we do in trig. Okay? And as long as you have the coordinate, if you want to know the sine of an angle, all you need is the y value of that coordinate. Okay? That's a definition. If you want to know the sine, you write the y value. If you want to know the cosine of this angle, as long as you know its endpoint, it's the x value. And if you wanted to know the tangent of this angle, you need both. You take the y value and you divide by the x value. All right. Now these are just the first 3 trig functions. There's also 3 other ones very similar. Does anybody know the other 3 trig functions? Okay, so Upi said the sine with the -1. We're going to talk about these ones that are above, but not today. Okay, but that's a good guess. These are very important, but not for today. Next one. So the other 3 are cosecant, secant, and cotangent. Okay, now that I've showed them, has anybody heard of those before? Mm-hmm. Okay, we abbreviate cosecant, CSC, secant, SEC, and cotangent, COT. Usually we just use the first 3 letters when we abbreviate, but for cosecant we can't do that because we already used the first 3. Okay, and all you have to do to get the 3 on the right is take the 3 on the left and flip them. Right? So if you wanted to pretend like there's a denominator, bless you, you could put that over 1. And what do you get if you flip y over 1? 1 over y. So the cosecant is just the sine flipped. Okay. What do you think the secant is?
1 over x.
Yeah. The secant is cosine flipped. And what about the cotangent? Y or x over y. The cotangent is the tangent flipped. Okay, so on a reference sheet, those 6 formulas are very important. Or at least if you remember the 3 on the left and just say, flip them to get the 3 on the
So
right.
is that why it's like the second, there's like sin -1, cosine?
Those are a little different.
They're different.
Yeah, that's a different,
But
yep.
no.
No, it doesn't, it's not these. No. You might think it would be because usually when you see a button with a -1, it means flip.
Yeah.
But that's what's confusing, the way they abbreviate it. It doesn't mean that. Okay, so we'll talk more about that. Those are called inverse trig. But not today. Okay, so does everybody have those 6 definitions? Okay, that's all we need for what we're going to do. Okay, these angles have a special name, so now's probably a good time to mention that. If you have an angle that's 0, 90, 180, or 270, it lands right on an axis. Okay, you saw that in the homework. And it's called a quadrantal angle. Okay. So if you see the word quadrantal angle, it just means it's 0, 90, 180, or 270. All right, so how do we actually do unit circle trig? We have all 6 definitions, but what do we do? Well, first thing you have to do is find that coordinate. If you can't find the coordinate, you can't do unit circle trig. Sometimes the coordinate will be given to you. Sometimes you're going to have to find it. Okay, first couple I start you out with, I'm going to give you the coordinate. So you're not even going to have to do step 1. It will be provided. Okay, in step 2, they're going to ask you for either the sine, the cosine, the tangent, the secant, cosecant, or cotangent. Whatever one they ask you for, just plug your x and your y value into the correct formula and write the answer. Okay, so find the coordinate, plug it into the correct formula. Okay, what we'll do to practice and start out is I'll do all 6. I'll find a coordinate and we'll practice all 6. Right, so the first one is the point 0, 1. Notice here, they're not telling you the angle. We don't even know what the angle is. Maybe you could figure it out. If you graph the point 0, 1 from the homework, you should know what the angle is, but you don't need to know it. And it's kind of similar to like if you met someone on the street and I just said I could describe their hair color, their eye color, color of their shirt, color of their shoes. I don't need to know their name to do any of that. I can just look at them and say all that stuff. It's the same idea here. We're going to say a bunch of stuff about an angle. Specifically, we're going to say what its sine is, its cosine, and so on. But we're never actually going to know the name of the angle or the size of it. Okay, we don't need to. All right. So here's x, here's y. Right, so let's start out with the sine of that angle. Okay. What letter do I use for sine? Y. What's y in this case? 1. Okay, that's it. So the sine of this angle is 1. How about cosine? What letter do we use for that? X. What's x in this case? 0. Sine and cosine are the easiest ones to do. Although we're just going to be doing arithmetic here with 1 and 0, so it's not overly hard. Okay, tangent is what over what?
Y over x.
Y over x. What's 1 divided by 0? Yes, undefined. Okay, you cannot divide by 0. Try it on your calculator, it won't be happy. All right, does anybody remember the name of the one that was across from sine?
Cosecant?
Yep, and I'm going to just use the abbreviation, cosecant. And once we get the 3 on the left, what do we do to each one of them to get the 3 on the right? Flip them. So what do you get if you flip 1? 1. Stays the same. Okay, how about my secant? Okay, and if you're stuck, think of 0 as a fraction. This is 0 over 1. It's undefined when you flip it. It becomes 1 over 0. Okay, and cotangent. Well, it would be 0 over 1, which is what? 0. You can take 0 and divide by 1. That's fine. Okay, so on the test, this would be 6 separate problems. I did all 6 just to show you how each one works.
So
Yeah.
by flipping for like the sine and then
The cosecant, the secant.
Yeah, so we're not using a negative, or we're just flipping like if there's a numerator and denominator, hypothetically.
Yeah, you're just flipping like if this is y over 1, this is 1 over y. Yep. If this is x over 1, this is 1 over x. Just flip it. Don't put a negative in. Yeah. All right, let's try this one. Okay, what's my sine here?
Square root of 3 over 2.
Yep, sine is the y value. Root 3 over 2. Cosine? That's 1/2. And for tangent, we're taking y and we're dividing by x. So sometime I just imagine drawing a division right there. That's y divided by x. If I did that, what would cancel out?
2.
The 2's. I have the same denominator.
So it'd be square root of 3
Just-
divided by 1.
Yeah, just square root 3 divided by 1. You could put divide by 1, or you could just write square root 3. Okay, my cosecant. Okay, we're going to be careful when we flip this one. Okay, what do you get when you flip it?
2 square root of 3.
2 over the square root of 3. But what's wrong with that?
We can't have square root at the bottom.
Can't have a square root in the bottom. So what do you multiply by to fix it?
Square root of
Square root of 3. Okay, that goes back to algebra 2. We get 2 square root of 3 over 3. Okay, so make sure, just like in any algebra problem, if you get a square root in the bottom, we never leave that. This one's pretty nice to flip. What do you get when you flip a half?
2.
Just 2. And cotangent? Okay, we'll do it in 2 steps. What do you get when you flip it? 1 over the square root of 3. And when we fix it?
Square root of 3 over 3.
Good. Square root of 3 over 3. So again, what we just did right there, that would be 6 problems on a test. Okay, you're not going to have to do 6 things in the same question. Okay, any question on that one? Okay, same idea, same thing, except what's different about this?
I don't know the angle.
They gave you the angle. You don't really want the angle. What do you need?
X and Y.
You need x and y. So if you're not sure what x and y are for 90, although we talked about it at the beginning, make a sketch. Okay, you're on a unit circle. Where's 90?
Quarter 1.
The y-axis, yeah. Now if that's a unit circle and the radius is 1, what would be the coordinates for that? 0, 1.
How do we know the radius is 1?
Because everything we're doing in this section is on a unit circle. The whole thing is a unit circle.
So
It's always 1.
units, yeah.
Yep, always 1. Okay, any question on how we got 0, 1? All right, now this is going to be really quick. Okay, what's my sine?
1.
My cosine?
2. 0.
And my tangent, just imagine dividing these two.
1. 0.
When you're dividing by 0, that's undefined. Okay, undefined. Okay, my cosecant, 1. My secant, undefined. I think we already did this one. This was the first problem I gave you. And the cotangent? 0. This one, let's just find the coordinate. I'm not going to go through all. We could go through them. They're not that hard. But where's 270?
The negative y.
The negative y. So what's the coordinate for that? 0, negative 1. All right. Sine?
Yeah, negative
Cosine?
0. Undefined.
Tangent?
Undefined.
Dividing by 0, yep. Cosecant? Yep, negative 1, when you flip it, stays exactly the same. Secant? Undefined. Cotangent? 0. Remember, this is negative 1 over 0. When you flip it, it's 0 over negative 1. Okay, be careful on those. Don't make little mistakes. They're simple, but don't make stupid mistakes. Okay, any questions on that? Okay. We could do the same thing if it's in radians. If you don't like radians, change it to degrees, and then it's just like this problem. So if you get something in radians and you don't like it, change it to degrees, and then do it. Okay, for tonight, every problem I give you is either going to be here, 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 or here. Those are the only coordinates you know how to find right now. 1s and 0s. Okay. We'll talk about other ones later. Okay. Also, same thing, if you get a negative angle, you can always add what to make it positive. Coterminal, you add 360. So if you don't like that, make it that, and we just did that problem. Okay, add 360. Okay, so the homework, it's on the first part, that's the angular velocity and arc length, page 324, 56 to 59, and 70 and 71. Okay, on 335, okay, I want you to do 1, 5, and 8, okay, whatever the book directions are. And I also want you to do what we just did. Find the 6 trig functions of 1, 5, and 8. So I want the sine, the cosine, tangent, secant, cosecant, cotangent. Okay. And also find the 6 trig functions of 3 pi over 2, 2 pi, and this coordinate. Okay, so make sure tomorrow I should see 6 answers for 1, 5, 8, this one, and this one. Okay, assign all 6 for every one of these. Right, so we'll take a look at that tomorrow. Okay, don't forget, I'll be here for extra help. And if you still have a test to make up, that's got to be done by Friday. So come soon.